so we have this intermediate value theorem, which I will often abbreviate IVT. And I think at the end of the day, it says something very obvious. Okay, we'll read it, and then I'll tell you in plain man's terms what it means. So if a function is continuous along the interval from A to B, so I need to somehow connect A and B without any jumps, any holes, any taking my pencil off the paper. So I can do something crazy, or I could have just done it with a straight line. Who cares? But the fact of the matter is the function has to be continuous from A to B for this to even apply. And if k is some number between f of a and f of b, so k has to be some number between. It can be way high up, it can be way low, it can be halfway in between. I'm going to put my k value there. So what this says is there has to be at least one c value between a and b. So essentially one x value that's c, one x value between a and b, and I'll put it, well, I can't really just put this anywhere because I have to figure out where it actually is. There has to be some c value so that f of c will equal that k value. And at least one. There could be multiple. So if I put my k there, which I did, my c value is really pretty much right after a. I'm going to put k1 and c1 because that's just one example. And so we have to have at least one point that really crosses that k marker, is what it's saying. If you put your k up here, so if you, I'll do k sub 2, you might have multiple c values that do this. So you'd have a c value, gosh, I have a c value here, a c value here, a c value here, here, and here. So that particular k value has 5 c values that do this, which is fine. It just says at least one. Okay? Does that make sense? So pretty much, plain man's terms, all it's saying is if you have a continuous function from A to B, every y value in between has to get hit along the way. That's it. Somewhere. Has to get hit at least once, if not multiple times. And you should be able to wrap your head around how a discontinuity would make this intermediate value theorem null and void. Because if you were going from f of a to f of b, and it wasn't continuous, so you did something like this, you can see what the trouble would be, right? There are some k values that got skipped. Yes? And so the intermediate value theorem would be null and void because the preliminary information that has to be true first and foremost is that your function has to be continuous along that interval. Okay? You always want to check for that first. And as long as it is, then any k value, any y value between the two that you're starting and ending with has to be touched at some point. Good? Okay? So it's pretty obvious, I think, that that would have to happen. It's just really putting the obvious into confusing words. All right, so you'll have to explain a lot, and your explanations as to why a function must have a 0 in the given interval. Now, this is focusing in on 0. But essentially, your interval is starting at 0. 0 what? If 0 is the x-coordinate, what's the y-coordinate? -2. So the interval starts at 0, -2, and ends at 1, 2. And most importantly, f of x is that preliminary information that always has to be true is that your function has to be continuous along that interval, right? Are we sure that this function is continuous along this interval? Yes, mainly because it's a polynomial function and they're always continuous, right? And f of x is continuous along 0 to 1. So we know it's continuous, so that's the preliminary information that has to be. Based on where our interval is starting and ending, why do I know it must have a 0 in between those 2 points? How could we put that into words, Olivia? Very good. It goes from a negative y value of -2 to a positive y value of +2. And because it's continuous along that, stretch of time from 0 to 1 on your x-axis, every y value between -2 and +2 has to get hit. At least once, if not more than once. Yes? So, how can we concisely put that in words? Interval starts at -2 and ends at 1, 2, and it's continuous along the way. So, since it starts with negative y value and ends with positive y value, zero must be reached along the way. Okay, the next exercise ups the ante a little bit. From a plain old polynomial function to a function that is partially rational, partially trig. Yes? So let's start with the continuity. Because if you don't have the continuity from 1 to 3, you can stop the problem right there. So, is this function continuous from 1 to 3? So this is just a rational function with an asymptote where? 0. A horizontal asymptote where? Small over big technically, right? Degree of 0, degree of 1. So an horizontal asymptote there. It's got a negative out in front and a 4, so it's been stretched vertically, who cares? And it's been flipped vertically. That does make a difference because where the parent graph would be got flipped, and the parent graph on this side would have been down here, got flipped, and it's stretched vertically. But the question is that continuous from 1 to 3? Here's approximately 1, here's approximately 3. So is that continuous from 1 to 3? Yes. Plus, okay, now tangents. Anytime you plug in from 1 to 3, you're going to be taking the tangent of pi over 8, which would be here-ish, to 3 pi over 8, which would be here-ish. At any point in time, in any angle in between here, am I going to have an undefined? No. You only get to tangents of undefined when you get up here. So between 1 pi over 8 and 3 pi over 8, this is also continuous. So you can start with that. Since f of x is continuous along 1 to 3, and we'll go back to the starting point. What's f of 1? If I plug in 1, that's going to be -4 plus the tangent of pi over 8. Oops. Now, you don't have a calculator. You also don't know what the tangent of pi over 8 is. But you do know what tangent's behavior is as it travels from 0 up to pi over 2, don't you? At 0, what's the tangent of 0? Tangent of 0 equals 0. The next one you know is pi over 6, which will be slightly past pi over 8. So the tangent of pi over 6 would give you, what's that? Root 3 over 3. And the tangent of pi over 4 gives you 1. What is happening to the tangent values as you climb? How are they changing? Say it out loud. What would you say? Increases. Tangents increase indefinitely. If you don't like the values, think about what your tangent does from 0 to pi over 2. It increases indefinitely until it gets to pi over 2. So if that's 0 and this is 1, we all can agree that the tangent of pi over 8 is somewhere between 0 and 1. Yes? So it's a pretty small positive. Can we say that? So if you take negative 4 and you add something that's between 0 and 1, are you going to be in the negatives or the positives? What did you say? You're still in the negatives. You were at negative 4 and you only added back a little bit. So you're still in the negatives. We don't really care about the value in this case because remember, this set of instructions wants to know why does it have to have a 0? Well, it's because the interval starts with a negative number. And if I plug in 3, it's going to be negative 4/3 plus the tangent of 3 pi over 8. Which is negative 1.3 repeating. And again, we don't know about 3 pi over 8, but I do know that 3 pi over 8 is slightly past 2 pi over 8. You follow? And so if that one equals 1, and it's like halfway between 2 pi over 8 and 4 pi over 8, which has like a gazillion and 1 as its answer, right? You're actually adding back, and this one I would probably say use a calculator because it's got to be more than 1.3 technically, and it is. You would find on your calculator that it is. The tangent of 3 pi over 8 would add back more than 1.3, and you'd end up with a positive number. So maybe I'd write calculator there. This one you can logically still see that you're getting a negative. This one you wouldn't know for sure, unless we had a calculator. So the fact of the matter is very similar to the last one. Since it starts with a negative and ends with a positive y value, it must cross a y value of 0 in between. Okay? All right, jump down to the next one. And here you will have some sections that say to use your calculator. So we want to first and foremost make sure we're in the right mode. And unless you see a degree symbol, the assumption is that we are in radians. So approximate where the 0 would be in the interval from 0 to 1. So we're just going to plug in that function, tan of theta plus 3 theta plus 4. And we only care about the x interval from 0 to 1. So on your window, 0 to 1 on your x-axis is all we're looking for. And we're trying to find where the 0 is. So that's on your y-axis. We really, negative 10 to 10 would be fine, but we just need to surround 0. But I'll leave it negative 10 to 10. And so here we are from an x-coordinate of 0 to an x-coordinate of 1. And it wants us to know where the 0 is. Did I type something in wrong? Tan of x plus 3x plus 4. Mode, radians. What would you say there? Where's the 0? Right, I would say it's not there. Tan of 0 is 0. Why don't, it's almost like it's a trick question. Why don't I remember this one from the request? I would say Mitch is right. There is no 0. Okay. Did anyone give them something different? Hold on. Just to see. Okay, degree didn't really change anything. So this, I guess I would say, is kind of like a trick question. There is no 0. Which makes sense because when you plug in 0, you get a y coordinate of 4. And when you plug in 1, you get a y coordinate that's even higher. So it doesn't actually cover 0. Hopefully we don't have that in the next exercise, because otherwise there's no way. I just don't remember this. So here we are again, window from 0 to 1, and then who cares about your y? Here we go. We're going to approximate. Now if I'm just looking at that, knowing that this is from 0 to 1, I'm going to guess it's around 0.5, right? But second trace 0, and then go left bound, get to the left of it, which is slightly under it in this case. Get to the right bound, which is slightly above it in this case. And so we've just set up our interval to say, okay, where is it crossing 0 in between here? 0.49. Root featured around to 4 decimal places, 0.4918. Any questions? Okay. On the back side, I'll just do one of each of these. Verify that the intermediate value theorem applies. So you first need to verify, and I'll do this one. You first need to verify that this function is continuous, okay? If I factor out an x, and I have an x plus 1 over an x minus 1, where is this function discontinuous? 1. But based on your interval, which is going from 2.5 and 4, do we care about the discontinuity at 1? No, because it's out of interval. So number 1, this is continuous along that interval. Verify that first, and then pretty much find the c value. So where is that x value when we will cross 6? Yes? So you'll just take this and set it equal to 6. So x squared plus x over x minus 1 equals 6, cross multiply and solve. Okay? It's very weird that they use 6 there, because 6 is outside of the interval. Usually you want to show, I might have copied that down wrong, but the fact of the matter is you just set it equal to it and go from there. And on the last one, show that for all spheres with radii in this interval 1 to 5, so any sphere that has a radius of 1 all the way up to any sphere that has a radius, I don't know how you guys want to draw your spheres. Just give it a 3D look. Any sphere that is, those sizes are in between, one of them will have to have a volume of 275. Do you know your volume formula for a sphere? Probably not, because it was always on your Regents reference sheet. So in the case of the 1 radius, it would be 4/3 pi times 1 cubed. In the case of the 5 radius, it would be 4/3 pi 5 cubed. This number, when you put it on your calculator, will be less than 275. This one is going to be greater than 275. So it stands to reason that somewhere in that growth period, it's going to cross a volume of 275. Okie doke? All right. Homework's there at the bottom. Wait. Homework is book work. And then I have 5 multiple choices as well. Okay? Just to give you a little feel for